lecture, we discussed about stability analysis of beam column, where both the bending and the axial compression were due to intentionally applied loads. In this case, the bending was the primary effect and we used governing differential equation for plotting the load displacement curve. In a beam column, bending and axial compression usually proceed simultaneously. However, the bending deformation can be assumed to be independent of axial deformation as long as deformation in general remain small. The analysis of beam column by energy method is therefore similar to the analysis of axially loaded member. That is, the energy of axial compression is omitted and only bending energy is considered. Let us discuss energy method, that is Rayleigh-Ritz method for the beam column with laterally distributed load. Beam column with distributed lateral load. Here in this case, if you see, the beam is subjected to axial load P as well as transverse load W per unit length. So, we will have to find out the load deflection curve. So, for this, this is L. So, for this we will use Rayleigh-Ritz method. Previously, we wrote the equilibrium equation by equilibrium method. We wrote the equilibrium equation by taking the part of this column and we took the moment about certain point and we wrote the equilibrium equation. But let us we solve this problem by using Rayleigh-Ritz method. So, what exactly the Rayleigh-Ritz method is? Here we assume a suitable shape function for the deformation of the system, and next step we find the total potential energy of the system by using this assumed shape function. Then we minimize the total potential energy, that leads to the equilibrium configuration. So, earlier way of finding the equilibrium equation was through equilibrium by writing the equilibrium equation. In the bent up configuration, we took the part of a beam column and we wrote the equilibrium equation. But in this case, we will be finding the total potential energy of the system and we will minimize this total potential energy and we will get the equilibrium equation. How it is done? Let us see. This is the beam column. Here the strain energy stored in the member, we will find the total potential energy is the strain energy stored in the beam because of the bending, and one part is external work done. Both things we will have to add to find the total potential energy. In this case, let us strain energy stored in the member, the strain energy stored in the member, it is U is equal to integration 0 to L m square dx divided by 2EI, implies U is equal to EI by 2 integration 0 to L d square y by dx square whole square into dx. And then external work done is because of this load and because of this load. So, two parts. So, that you can write here external work done is equal to minus W into integrating 0 to L y dx then minus p by 2 into integration 0 to L dy by dx whole square into dx. So, there should not be any confusion of writing this expression. This is easy, that load into deflection, that has been integrated, work done is equal to W into Y, that has been integrated 0 to L. This is correct. Now, here the end shortening value, end shortening means what? End shortening, because of this application of the load, the end will get shortened. That value is half into integration 0 to L into dy by dx whole square into dx. So, when this end shortening is multiplied with load P, then we will be getting the work done. So, that has been done here. So, this is the strain energy stored, and these two things, this is the external work done. So, if we write both U plus V, this becomes E I by 2 0 to L d square y by dx square whole square into dx minus W into 0 to L into y dx minus p by 2 into integration 0 to L dy by dx whole square into dx. So, this is the expression of the total potential energy. Now, in Rayleigh-Ritz method, we will have to minimize the total potential energy, and we will have to assume a shape function. That assumption will be done as per the boundary condition. This is a simply supported beam. So, the deflected shape can be assumed as the deflected shape may be assumed by considering the boundary conditions. What are the boundary condition? That is, bending moment at the end is equal to 0, then deflection is equal to 0. So, we will have to assume a sine function, so that if we will do double time differentiation, automatically it will come again sine. So, bending moment will be 0. So, is the best thing is y to assume y is equal to delta sine pi x by L. So, this is the assumed shape function. Then if you substitute this y value in this total potential energy, I am writing directly U plus V comes out to be EI del square pi to the power 4th divided by 2L to the power 4th and integration 0 to L sine square pi x by L into dx minus W into delta integration 0 to L sine pi x by L into dx, this minus p delta square to pi square divided by 2L square into integration 0 to L cos square pi x divided by L into dx. So, this is the total potential energy. EI, if you substitute it, if you twice differentiate and square, automatically this will be pi to the power 4th, then this is, and this is all right. This you can check it. Now, if you use the definite integral value, these known values, use definite integrals, this is 0 to L integration of sine square pi x by L, integration 0 to L sine square pi x by L into dx. If you integrate, that will become the also cos square pi x by value, also this will be also same, this will become L by 2, and integration of 0 to L sine pi x by L into dx, if you do, it will come 2L by pi. If we substitute this thing in this expression, so the u plus v value will be, implies this u plus v is come out to be ei by 4 into delta square pi to the power 4th by L cube minus 2w delta L divided by pi minus p delta square pi square divided by 4L. For the system to be in equilibrium, this for the write it, for the system to be in equilibrium, this delta of u plus v by delta of delta is equal to 0. This is the Rayleigh-Ritz method. This we can use. This is the minimization of the total potential energy. If you substitute, if you differentiate, in fact, if you differentiate with respect to delta, that becomes, I am directly writing ei into delta pi to the power 4th divided by 2L cube minus 2WL divided by pi, because only delta is there, if you differentiate it will go, and minus P delta pi square divided by 2L, this equal to 0. So implies delta is equal to 4W L 4th divided by pi multiplied by 1 divided by E I pi to the power 4th minus P pi square into L square. So this is the delta value. So now we can multiply by 5 by 384 EI, and we can divide by the same. This remains same, so only this becomes cancelled out, becomes 1, multiply, and we will multiply with this, this becomes 4WL 4th by pi. This is the same thing, and we wrote 1 by EI pi to the power 4th minus P pi square L square. Then this is multiplied and divided, multiplied and divided. This is all right. So this delta you can write as 5 W L to the power 4th divided by 384 EI multiplied by 1536 divided by 5 pi to the power 5, and that will become P by PCR. So implies this delta is 5 L to the power 4th by 384 EI, and this value becomes 1. This value becomes 1. So, you can write multiplied by 1 divided 1 minus P by PCR. So, this one you can write delta by delta naught multiplied by 1 by 1 minus P by PCR. What is the intention? We multiplied by 5 by 384 EI. This is finally we will get this expression, which is represented as delta naught. This delta naught is the deflection when only lateral load is applied. For a simply supported beam, when uniformly distributed load is applied, that time the deflection at the center is 5 W L to the power 4th. This W is rate of loading, and 5 W L to the power 4th divided by 384 EI. So, that is delta naught, and which is multiplied by 1 divided by 1 minus P by PCR. So, this deflection is when beam is subjected to both transverse and axial load. So, this I am writing when this is the deflection when beam is subjected to both transverse and axial load. So, with this let us go to the bending moment, how it is affected by the axial load, because when the beam is subjected to only transverse load, only uniformly distributed load, there is certain moment will come at the center. But along with the transverse load, when there is axial load applied, how this bending moment is affected? Let us discuss this. So, the bending moment is also affected by axial load. Okay, this is all right, bending moment is affected by axial load, but how? The maximum bending moment at the center of the beam is, we know when there is only uniformly distributed load, we know WL square by 8, when W is the load per unit length. But in this case, because of axial load, the additional moment will be P into this delta. Delta is the mid-span displacement. So, implies M max is equal to WL square by 8, and we will substitute this delta value. So, this becomes 5P WL to the power 4th divided by 384 EI and multiplied by, this is P by 1 minus P by PCR, because we derived this delta value, we derived this value. So, that we wrote here. Now, if you will take the common WL square by 8, if you will take common, this will become 1 plus 5P L square divided by 48 EI multiplied by 1 minus P by PCR. So, this is all right. Now, you can write WL square by 8 into 1 plus this 5 PL square by 48 EI, that can be written as 1.03 P by PCR. This you can check. This is the simple thing. Previously also similar thing we have done. And if you multiply 1 by 1 minus P by PCR. Now this becomes WL square by 8 multiplied by 1 plus 0.03 P by PCR divided by 1 minus P by PCR. This is the bending moment, this is the maximum bending moment when there is no axial force. So this is what? This is the amplification factor. This is the amplification factor for M max. We are calculating M max. So amplification factor for finding this M max when axial load is applied along with the transverse load. This is all about. Thank you.